For coming today again. We'll continue talking about IoT. So what we started 2 weeks ago, talking about the new protocols were developed for IoT, right? So for example, we said HTTP is a big protocol to use for IoT devices. Why is not useful? The header is big and MTU or the data is big. Okay, so we came up with code, for example, right? Okay, and then for OSPF, okay, it's not what we came with. We're going to talk about today, right? Right. So last week, which protocol we spoke about? Refresh your memory. So last week we spoke about 6 low band. So instead of IP6, okay, we have 6 low band. We explained it last week. Today instead of OSPF, we're going to use Core. Okay, will replace HTTP, right? All right. So we're going to talk about all of these protocols. So this is in one layer, this one in one layer, the application, right? And this in the network. And this is also in the network. Okay? But this is like the router side. Right? And this is at the host side. Okay, at the host side. Okay, so this is the network layer. This is at host side, and this is at the router side. Okay, for router. All right. So the typical technologies or protocol needs to be changed. How about in the physical layer? So in the physical layer, what usually we have? 802.3. What's 8.3? What is this? Ethernet, right? So we're going to replace it with 802.4, for example. Okay, 15.4, which is for the low, 15.4, for the low devices, for the lowest devices, right? So at each level, we have a different technology or protocol applied. Just to refresh your memory, in the OSI reference model, how many layers we have? In OSI? 7, right? So we start with physical, then data link, then transport, and application. Okay, the 3 could combine them and the application. So typically in the physical there is technologies like Ethernet, so for example 802.3, right? For wireless what we have? 802.11, right? Okay, for wireless. Alright, then you have the MAC at the data link layer. In the network what we have? What we have? OSPF and the router side and IP 4 or 6. And the transport what we usually have UDP and TCP. Okay. In the application, many applications, the most common one is HTTP, right? Okay, and there is SHTTP, right? And others, and FTP, FTP. Okay, there's many applications of it, right? So all of these, and you know how the data go. So the data how it goes, because you start from where? From the application. No, you start from the application, right? So what you do, okay, you start with the data, it's the HTTP, right? It has header and the body, you know, let's call it the body of the data, right? Then it goes down, okay, it's gonna go, for example, to the transport tree. So this the body will be here, the header will be here, this header will store it, and we're gonna add header 2, right? That's where that transport becomes bigger. Then it goes down, right? Right, goes further down, okay? So we have the body again, the header 1 coming from here, the header 2, and then header 3. This is at what level? Network level, right? Then it's gonna go down, same thing, it's gonna go, okay, it's gonna go, so the body gonna go here, and the header 1, header 2, header 3, and header 4. Then this long packet will go where? On the wire. It's gonna go in the wire, okay? It's gonna go to a router, for example. This is a router. Router has how many levels? 3. Physical, data link, and network. And from there, it's gonna go to the other side, right? To the other destination, right? All right? And let's say this is another destination. You're gonna start from the physical. The physical will read it and remove the last header. You're gonna go up without the last header. Now in that level, it's gonna move this header, gonna go up and until it goes to the destination. So as it's going in the network, it's becoming bigger and bigger, more information. As it goes up, it's becoming smaller and smaller, right? That's in a typical network. We're still going to have the same technique. The only problem, the old, or not the old, I can say the old, the protocols used for a full, strong devices, networks, it works nice for such devices. But you know what you're comparing a big server. Okay, it had like 16 gigabits of RAM. It has a very high processor. Okay, with what? With a sensor. So the sensor has a small RAM. Okay, it has small ROM. Right? It has small processor. Right? So these protocols cannot work. We have to replace it. So we started last week talking about one of the protocols, which is 6LoWPAN. We saw how we moved from full IP6. 6LoWPAN, 6 stands for what? IP. So IP was removed, IP6, but for low personal area network. So IP6, 6LoWPAN. So we say 6LoWPAN, okay, which is 6 means IP6 for low personal area network. For regular routing. Alright, and that works in what level? In the network layer, right? So at the network layer still we have there's two things. There's something runs on the host and something runs on the routers, right? Something runs in the routers. Okay. So what we call, this is also from the basics that you have heard from, what we call TCP, and there's a stack, protocol stack, right? So when you talk about, for example, we heard about TCP IP. What do you call this? Protocol stack. Why do we call it TCP IP? Why we call it UDP, for example, IP? Because these are the most common protocols, they are the main protocols in this stack. And this is not the only two protocols that are used, because there's a protocol at the application level, there's a protocol at the network level, there's a protocol at that network. We call this stack TCP IP, that's it. I mean, we call it the stack. Okay, it's not a protocol, it's a protocol stack, right? So, and there's there is IPX, SPX, another stack. We did not use it for a long time. And if you remember in Windows, we used to have something called NetBeaver. I think it's written like that, if I'm not mistaken, NetBeaver, right? The initial Windows, like 3.11 and 9.5, it came with a protocol called NetBeaver. You will be able to connect computers together. Okay, what is the difference between, for example, these two and this one? This we call it, okay, routing, or routed absolute protocol. This is not a routed protocol. What does that mean? That means the packets in these two stacks can go through routers. But packets from this network cannot go through routers. So for example, if I have a hub connecting two computers in here, and then I have a router, and they have another network like that, right? If I'm running NetBeaver, this is the router, right? This is the router, right? Connecting the two networks, right? So if I'm running NetBeaver protocol on these devices, I only can communicate within the LAN. I cannot go through the router for NetBeaver. But for TCP, IP, and IPX, SPX, I can go through the router. And the data can go through the router. So what we call it? Routed protocols. So this is routed protocol, routed protocol. Routed, what does it mean? Protocol could be routed. Okay? This is routed with ED. What is routing protocol? There is another term called routing protocol. What is routing protocol?
Dynamical.
It's the, no. So routing protocols could be dynamic, could be static. Okay? Routing protocol are the protocols running on the routers. Like REP, like OSPF, like Ripple, we're going to talk about it today. So they are protocols running on the routers. Right? It's kind of the operating system of the routers. So what does routing the protocol do? Create tables, learn about the situation of the network. So when the packet coming from a network, coming from this side, going to go to the router. The router from the network address can know which way to route it. Okay? So there's a difference between routing, know these terms, and routed protocols. Routing and routed protocols, right? So now, today we're talking about protocol running where? On the routers. So what their function is to route the packets to that network, right? So the most common routing protocols are REP and OSPF. We cannot use them in these low and lossy, no energy lossy devices. So they came up with something called Ripple. So that's what we're going to explain today. Ripple. Clear? All right. So next time we cannot use HTTP. HTTP is too big. We have to use something called CoAP. COAP. We're going to explain what COAP. Right? In the physical layer, we don't use Ethernet. You cannot have a sense of running Ethernet on it. You cannot plug an Ethernet card there. Okay? So we have, for example, ZigBee. As an example, I'm talk about ZigBee. Alright? And so on and so forth. Clear what we are doing now? Alright. So I hope it's clear. So it's very important that you have a good background about DCC, data computer communications. I hope you took 572 before. Everybody took 572. It's a core course, right? Who did not take it? Did not take it? Okay. So you know about the stacking all the time. I'm sure you do it in your undergrad at least, so you have a background about it. Okay? All right, so let's talk about triple, okay, and why we need it. So the unique routing requirements of IP smart object networks. We have to have a power consumption issue, okay? In the regular networks, do you have a power consumption issue? We don't, right? Right? We have it with sensors. A small form factor, very small, okay? Form factor means the way it was built, the device, the lock. So the form factor. Form factor for this could be, so this is like a key lock, like this is for my Suburban, this is the form factor. This is my Honda, different form factors, right? Okay, right? So everything comes to communication challenges like low speed, high error rates. Okay, a typical off-the-shelf available smart object will have only tens of kilobytes. So the tens of kilobytes RAM and flash, ROM, flash to save the data. So we cannot have regular protocols to manage these network. And the software in the smart object must not only be power efficient, but must be able to run small memory footprint. It has to be very few bytes, not kilobytes, not megabytes, not terabytes, right? And also we need to have auto configuration. Auto configuration, it's always good. But when it comes to the sensors and the small devices, it's much more important. Why? We are talking about hundreds and thousands and tens of thousands and hundreds of thousands of devices. If you're going to have a network to monitor a volcano, you might have 10,000 sensors, right? Are you going to go for every sensor to configure it, give it IP address and configure? You have to have a mechanism for auto configuration. So when it comes to this application, auto configuration is very important. It's very important. All right. I don't need to talk about the power consumption. We already spoke about it. Normally use media operating on low power communication standard. So we have low power wireless communication and power line communication protocols. Some low power link layers is the second layer, right? Second layer, designed for LLNs. You know what's low and lossy networks, the low energy and lossy networks that are working with Preble. So these are the 802.15.4. It's the LLNs. When it's 802.3, this Ethernet. Okay, 11 Wi-Fi. Okay, 5 token brain, and on different technologies, right? So such networks are also referred to as low power and lossy networks, LLNs. You always, when you IoT, you deal with LLNs, okay? And they are lossy, God knows a lot, okay? So we come to the routing. Okay, what's routing? You have many nodes connected, and they need part of different networks. You need to route the data. You need to route the data. So how can you route the data? So what is routing process in general? Routing is a process by which the network determines what paths. So routing is looking for a path. What is the route to go to New York? What path to go to New York from here? Okay? The message should take, right? So in traditional networks, any loss of connectivity triggers a desire to quickly to converge. So you have multiple routes. If there is a faulty route, what you have? Reconverge. You're going on 95 to New York, there's a big accident. So what you have to do? Converge, take an exit, take another highway, converge, right? Same thing in here. So a number of techniques such as fast routing, IP, MPLS, have been designed for link state protocols, such as OSPF and ISIS, sorry for the word. This is network ISIS, not bad ISIS, right? All right. So almost discipline for red OSPF, ISIS, all of this are available a long time ago. The action is seen overkill in LLMs. The way they work is overkill. Okay, so they cannot work. We have to look for smaller protocol. Okay, a preferred model should be under React. I mean, yeah, it's smaller, but we don't have to be perfect. Okay, we don't have to have the reaction that we have in these big protocols. So usually in these protocols, when there is lost by packets, or there is some routes are not working, you have to react right away within milliseconds that the user does not notice even that there is a break. In here, we ease it a little bit. We ease it because we don't have a hardware to do it. I mean, we have a weak hardware, so we could have under react to smooth over the transit loss of connectivity and have a confidence monitoring model. All right. So routing and LLNs should be able to self-manage to a large extent and be able to heal itself without requiring manual intervention. Right? Again, you're talking about a huge functionality, right? Much bigger than that. So the packet delivery ratio, PDR, packet delivery ratio. So when you're sending a message, the message is divided into packets into frames. So you don't notice as end user how many packets are lost. But not every packet went out of your computer to the destination, went through. Some of them get lost or destroyed or arrived erratic. What happens? Retransmission. You don't notice anything, you don't know anything because there's a mechanism to do that. Right? The whole network works together to do that. And that's what we call it packet delivery ratio. Okay? The link quality has direct implication on routing protocol design with respect to convergence time. All right, so we could ease a little bit in the convergence time, be easier in the convergence time, but due to the limitations we have. All right, so the packet delivery ratio over a low power wireless, as you see here, it could vary. Okay. Let's talk about Ripple. It's an open routing protocol for IP Smart Object. IP Smart Object, right? IP. All right. All right. And there's a working group called RON, routing over low power and lossy, and they wanted to come up with a routing protocol specific for LLN, low and lossy. Okay. The result of this working group came with Ripple. We read it Ripple, we write it RPL. It operates at the IP layer, so at the network layer, according to the IP architecture, and thus allows for routing across multiple types of link layers. Where is link layer? Below. Right? Physical link, right? And then it comes, so regardless of the physical architecture and the link layer, it will work independent from that. All right. So let's take a look at the Ripple mode of operation. So RPL is distance vector IP6 routing protocol, and it's specific for LLN. It's not for regular networks. We have to create something called destination-oriented directed acyclic graph. So in routing, what we are trying a graph, right? So the graph, so like the graph whatever. Right? Routing. So for example, if I need to send the data from the routing here to node A, it would go like this. Is there another route? It's the only one, right? Okay, because there are multiple routes, right? It has to build a table through the route how the data gonna move, right? So that's what we call it a cyclic. There's no cycles, and it's a graph, oriented directed graph. DODAG. Okay, we call it DODAG. So remember what is DODAG from now on is the graph. It's spelled DODAG. So a combination of metrics and constraints. So we are looking at metrics and constraints. So if I need to choose a route to go from here to here, I have to look at the constraints and I have to look at metrics. Okay? Let's take an example for that to compute the best path. So according to the metrics, right hand metrics, and left hand we have constraints. The protocol has to calculate best path to fit these constraints and required metrics. So example, find paths with best expected transmission values, value. So whatever, I need it to be, for example, 10 kilobits second. This is a metric. All right? And avoid non-encrypted links. So some of the links will be encrypted and some of them not encrypted. So what is the metric in here? I need it to be encrypted and I need it to be certain speed, for example, transmission rate. So what we call this? Metric. Constraint, find the best path in terms of latency. Okay? Okay, the latency. So what is the latency? Okay, this is metric. Okay? And what is this? Okay, let's go back like this. So what is the metric in here? It's the speed. What is the constraint? Don't go through not an unencrypted layer. In here, so I'm looking for the latency. That's the maximum latency I could have. Okay, why avoid battery operated nodes? So okay, power. Okay, constraint. So when you determine the path, you have to look at set of constraints and metrics required for that path, and choose the best path according to that. All right? You want to go to New York? All of you are invited tonight for a lunch in New York with me. I'm paying. Okay, but you have to go by yourself and you have to be there by 7 p.m. All right? So what is the constraint? What is the metric? You have to be there by 7 p.m. Okay, what's the constraint?
How are you going to go bus train?
Okay, the constraint is you cannot come riding. So you cannot ride the car, you cannot ride the train. You cannot, okay. So either you walk or swim. And you have to be by 7 o'clock. So what's the best path? What is the best path? Okay? Alright, this way I'll eat by myself. So I make sure I eat by myself, right? So the graph built by Phil is a logical routing topology built over a physical network to meet a specific criteria. So we are looking at the criteria. So multiple routing topologies, graphs, active at the same time. So we have like many nodes, we could have multiple graphs at the same time. Multiple graphs, right? That means multiple what? Paths. Okay? Or plans for paths. Used to carry traffic with different set of requirements. A node in the network can participate and join one or more graph. And that's we call it triple instances. Okay? So this could join multiple plans. This could join multiple plans, right? At the same time. Clear? The idea is clear. The most important thing is the ideas.
Distance vector, what does it mean?
There is two general routing protocols which we explained in DCC. Okay, distance vector, the way you built the routing table, and there is another technique. So if you go to any DCC book, you could take a look at it. Okay, so there is two general techniques. Okay, distance vector, and there is another one, how to build the tables. It depends on the metrics. So for example, you could measure, for example, the link weight between the two nodes. All right. What is the link node be, for example, the shortest? It could be the fastest. It could be the least hop. Okay, the least hop, the number of hops in between. So it's a general. There's two general techniques for routing. Okay, I don't have time to explain it now, but we could review, right? Thank you for the question. Okay, do that is the graph, right? Building the process. So how we build this graph? That's the map. That's the table, right? How we build that? All right. So the graph building process starts at the roots. Okay, the roots. Remember last time when we explained the network is we have like this here. We have the root, and here what we have something called edge router. And inside the network what we have routers or host. Remember? Okay. So how we build this graph? How this graph is built? So there could be a multiple routes configured in the system, multiple route, and the ripple routing protocol specifies a set of a new ICMP v6. That's the reason why I had to go through IP6, okay, just, you know IP6 very well now, right? You know how the addresses are formatted, how is the packets are formatted, how we transmit the data, right? You studied, right?
Yes.
You went over that. And then we went over ICMP. What's the ICMP? Internet Control Messaging Protocol. Remember in the last lecture when we explained IP, we used it to transmit the control messages. Remember, in the communications, there is two kinds of messages. One is real data communicating, okay, and one is control messages to control the whole operation, right? Exactly like in this country, there's two kinds of people. There's regular people like us, and there is rulers or government, which is people controlling the thing, okay, controlling the whole society, right? The same thing in the network. It's like a kingdom. It's like a country. There is hosts that communicate, do everything, regular data, and there is messages for controlling the whole operation. So if there's a router is not working, how can the system know the router is not working? Message has to go from the router to somewhere. That has to go through another communication link, for example, using ICMP version 6. Right? So it's very important to understand IP6 how it works and IP4 to be able to understand this. You have to start from there, you start with IP4, IP6, then we are looking at the new protocols used in here, right? We will explain this and go to the video and go to the lecture. So the control messages to exchange graph related information. Now to build the table, the information. We are not, this and this now we are not exchanging data or the reading of the sensor. We're exchanging what? Information, how to build the table. What is the host ID, what is the location, what is the brand, what is okay, how it will go through the routing table. So each one of these, if it's a router, will have what? A routing table. The edge will have a routing table. And this routing table should be dynamic. Right? So if the router from here to here is going to go through this, what will happen if the battery of this node is gone? There is no path. So the routing tables need to be rebuilt again. Alright? So in here, what kind of information again we're exchanging is the information to build and control the routing tables. So what we have to do first to build the graph, the table, the map, call it whatever you want. Once it's built, data could exchange. If something happens to these nodes or the data gets, for example, the nodes get, for example, battery depleted or the router get corrupted, or then again we have to rebuild the tables again. It's ongoing process all the time, right? So that's what this Ripple is all about how to build these maps, okay? These maps, okay? So how we build these maps, how we educate these nodes, how we build the tables, through what? TV? We make the nodes watch TV, for example? Huh? Through messages. Through messages, running over ICMP6. Okay, what are the messages in here? So these messages are called DIS, Do Dot Information Solicitation. So the node, okay, it will look for solicitation. I am a host. I'm looking for a router. I need a router nearby me that I could send the data. I need to get the information solicitation. So what does it do? It sends a message called DIS, Information Solicitation. Oh, Information Object. Okay, DAO. Okay, Destination Advertisement Object. So the router, what does it do? The router does not solicit a node. Advertise. I'm here. Advertise itself. I'm here. Anybody would like to join me? Can join me. So what does it send? Advertise. Host. Send solicitation. Right? Right? So this communication happens until we build all the tables.
Which one sends the information object?
Information object we'll talk about in a second. Okay, there's 3 different messages. We'll see how they work now. But I'm giving you example now, router. If you think router, which one has to do?
3.
Huh?
3.
What?
Advertisement object.
Advertisement,
Yeah.
host,
Solicitation.
solicitation, right?
Yeah.
And then building the objects. We'll see how they are used exactly with examples now. All right? Clear so far? So what we are trying to do now? To build a graph. How we build the graphs? They have to communicate together. Who has to communicate together? The hosts and the routers. To do what? To build the tables. How we build the tables? By exchanging information. How they exchanging information? By using the ICMP. What they do in ICMP? They exchange 3 types of information: solicitation, advertising, etc. We're building the tables. Okay, that's the general idea. Details comes. All right. So the root starts. What is the root? The top one. It's kind of edge route. Okay. So the root starts advertising the information about the graph using the IO message. What is the IO message? Information object. So it tells that I am the router. That's the message sent. Send advertising. So this is used for advertising and this for advertising. But this is by the router. I just answered your question, right? Okay. Neighboring nodes of the root. What are the neighboring nodes? All these are neighboring. Root will receive and process the IO message. Because they are neighbors, you are my neighbors. Now I'm shouting, I am Dr. Ab's name. Did you hear me? This is my DIO message. So what are you going to do? You're going to respond. What are you going to say? So what? Right? So what in this case, right? So, and the process DIO message potentially from multiple nodes. Alright? Okay, why multiple nodes? Because if it's too far, it could be related to it. Right? So sometimes a host receives a DIO message, re-advertises again, that goes further, deeper. Right? So node to decide whether to join the graph or not, depending on the objective function. We'll talk about it. So now you receive an advertisement, right? A host, right? So I am a router. So you have to decide, shall I join this router or not? Because there's multiple options, there are multiple routers in the network, right? So it will depend in what? In the objective function, we'll talk about it. Objective function, which is what? Constraints and metrics. We'll talk about it, right? Characteristics, okay, advertised path, cost, is too far to close the cost, and potentially local policy. If there is a local policy in that node, join, not to join, all right? All right. So the node computes the rank. What is the rank?
The highest priority.
Who's the rank? So it starts from rank 0. The further you go, rank 1, rank 2. The further you go, your rank increases. The number increases. So the highest is rank 0. As you go, the number increases, but it kind of decreases, but the number increases, right? So the rank of itself within the graph, which indicates the coordinates of the node in the graph curve. Clear? Yes.
So DIO messages are sent by each of those nodes?
What?
DIO messages.
By the routers. That's what we said, by the root router. The root router.
But then in the second point it says that the neighboring nodes will receive and process from
Yeah, so the root router will advertise on the IO. Okay? Everything will receive it. So this will decide, shall it join or should not join? Why? Because as you said, you could have multiple roots. You could have another root in here. Root. So this advertises and this advertises. This hears both them. Has to decide, shall it join root 1 or root 2? Depending on what? 4 things. The objective function, the characteristics, the path cost, and the local policy. Alright? Clear? Thank you for your question. Okay? The first thing also has to know that the rank. So the rank in here is 1, 2, 3. So 0, 1, 2, 3. The rank is 3 as well. Okay? The rank of this is 1, and so on and so forth. The closer will be, you have to calculate how far. So if the rank of this from root 1 is 5, and the rank from root 2 is 2, which one should join?
2.
2 technically, unless there is other reasons. Right? Right? Alright, so what is the rank? As a router, it starts advertising the graph information with a new information to its neighboring peers as a leaf node. It simply joins the graph and does not send any DIO. So DIO is sent only by routers and the root, right? Messages. The neighboring peers will repeat this process and do parent selection. So each one has to have a parent, okay? Okay, router addition and graph information advertising using the DIO messages. Right. In this formation, each node of the graph has a routing entry toward what? Toward its parent. Routing entry. So routing stuff from here up. So it goes to where? To the root. So technically, if this one would like to communicate with this, how it will happen?
Go to the parent node and then
Add parent to the root and then it's sent. Okay? Maybe there's 2 ways. That's the simplest way, right? So in this way, who has the tables?
the parent node.
The root. Okay? The node will know it's only parent. Right? No parent, send it up until it goes to the root and send it 10 down. Right? Okay? So the leaf nodes can send data packets all the way to the root of the graph by just forwarding the package to its immediate parent. Immediate goes to the root. The root has a table, now knows how to send it to the destination. And by the way, if you're talking about the sensors in here, okay, what kind of communication usually happens? Mostly, sensors collecting the data, gonna go to the root, and the data gonna go to the server somewhere else, right? So most of it goes up. Or some instructions will be sent from the root to the leaf. Turn on, turn off. Okay, for example, this leaf measures the temperature every 1 minute. Now measure the temperature every 5 minutes. But most of the data goes from where? From the sensors collecting and goes up. Some scenarios that we need to send information. We're gonna send not information, instructions to where? To the sender, to the leaf, right? Which is less. In a much lesser situation, we need to have node connect with a node. Why node needs to connect to a node in this application? Very rare, right? Few rare cases we'll talk about them. But mostly the data going like this, and it's gonna go to the sink, right? Okay, sink. That collects the data, right? So if this, for example, measures the temperature every 10 minutes, let's say. So at time 1, it will know the sensor what is the temperature. It's gonna go up, right? That's what the application mostly, right? Right? Think about these nodes like cameras. Small cameras, footprint for our cameras. So usually, where is the data? At the cameras, you are reading every, for example, 10 minutes it takes a snapshot, we'll send it back to the database. Very few times, let's say you have 5 doors at your house. It's recording, going to the root, and then going to the server where it saves it, right? When you need to view it, you view it from the server. In very rare case, once every full moon, you need to send data to, for example, this camera till it's zoom in. Right? Right? Is there a reason why a camera needs to communicate with a camera? No. Unless for management issue, right? You understand? So most of the data gonna go like that anyways, right? All right. So there is multiple point to point forwarding model where each node in the graph has reachability towards the graph. Multiple points, multiple nodes, you're gonna go to points, right? All of these we're gonna send the data to, so it's multi-point to one point, right? which is upward routing. Each node in the graph has a branch that is relative and represents an increasing coordinates of the relative position of the node with respect to the root. So as we go down, the rank will really explain that. The notice of rank is used by Ripple for various purposes, including loop avoidance. There is an algorithm for loop avoidance. You have to avoid loop, right? And there is a multiple point-to-point flow of traffic called up direction. So up direction, which is the most needed one, up direction. So that's what will happen in here, as you see. Okay, this is the root, and then the data. So for example, okay, in here, from here, you're gonna go from here. This is the parent. This has two parents. We go here and here. Okay, this has only one parent. How you know it's one parent? Because the rank of this is higher than the rank of that. So this is a parent because it has a lower rank. This is a child because it has higher rank. Okay, and then goes the direction. Okay. So we explained about the DIO, how it starts. The DIO starts, then it responds until you build the whole graph. So now tables, route tables will be included in these devices. Clear? All right. So the DIS message. What is DIS in official memory? Okay, DIS, which is information solicitation. Okay, information solicitation. Okay, is used by the nodes to proactively solicit graph information via DIO from the neighboring nodes should it becomes active in a stable graph environment using a pole and model of retrieving graph information or in other conditions. So we're trying to get information about the graph. There is also a need for the traffic to follow in the opposite direction, which is down direction. Okay, this traffic may originate from outside, from the server, okay, and goes to the root, and then it has to go to the leaf. All right. This requires a routing state to be built, and every node and mechanism to populate these routes. This is accomplished using the DAO, this destination advertisement object, which is the third message, destination advertisement object messages. So let's talk a little bit about traffic down direction. This requires a routing state to be built at every node and a mechanism to populate these routes. State means memory. State means a memory. You know what is before you, what's after you. This will be built in the route. Okay, and we're gonna use destination advertisement object. Okay, DAO should advertisement object usage are used to advertise prefix. Okay, what's a prefix? Each address has a prefix and suffix, right? All of them are going to have the same prefix. Okay? Prefix reachability towards the leaf nodes and support for the down traffic. These messages carry prefix information, valid lifetime, and other information about the prefix. Okay. As each node joins the graph, it will send DAO message to its parents, to the parents. It could have 1, 2, 3 parents to get a set information from that. Other way to do it, a node or a root can pull the subgraph, and try to build a route from it to send the message. And each node receives the DAO message. It processes the prefix information and adds a routing entry in the routing table. Okay, checks the prefix, all right, and adds the route. So, for example, it goes from here to here, checks the prefix, and then from the prefix can know which direction it has to go. Then it tells you have to go to this route, and then it's routing. So we will see exactly what set down. This continues until you go to the leaf. All right. Now. The nodes are two kinds. There's something storing nodes and non-storing nodes. Storing nodes, that means could store routes as a memory. Routing tables. Okay? So each node can have a table, and from the table could direct the messages downward. I mean, for upward is easy. Why? Because upward has to go where? To the parent. Until it goes to the root. But downward it has to know where to go. So if it's a storing node, then it will have a routing table to direct the packet to the leaf, right? You're talking about like deep graphs. The other things, so we spoke about up routing, down routing. Now we talk about point-to-point communication. When a node sends a packet to another node within the LLN network, the packet travels up to the common ancestor. Common ancestor. So common ancestor means. So if this would like to communicate with this, where is the common ancestor for them? Is it this or this? Goes to the common and okay. And since this is a storing, then it has a routing table again. Okay, it goes to the common, does not need to go all the way to the root, it goes to the ancestor, and then it can be directed to down. Okay. So the common ancestor, at which point it is forwarded in the down direction to the destination. If the common ancestor only is the root, that's fine. You can go up to the root and then goes down. Yes?
Can the common ancestor be a non-storing node?
Can be non-storing, yes. So if non-storing, always you have to go to the root. So in this case, for example, we were able to go only to the common ancestor, common parent. Why we are able to run it back to here? Because this is a storing node. It has a table. It knows how to direct the packet back to the leaf. But if these not storing nodes, what will happen? The root is the only storing node, so everything has to go to the root. Right? So the question is, which is better, to have a storing or non-storing?
Depends on the application.
Depends on cost.
Huh?
Depends on cost.
Well, I mean, having a storing node, that means the node is more expensive, but it will be faster network. Okay? If it's not the storing, the node is very cheap. Cheap. But it will be, so the load will be on the root, right? Well, okay, you answered the question right. That means you're following me. I'm happy. First time I feel that. All the time. Okay, so multi-topology routing, multi-MTR, multi-MTR. So thanks to the concept of the do that, instance identified by instance ID. So what we said, that these nodes, we could have multiple graphs, multiple instances, right? And the node could be part of two or more, one or two or more instances, right? And each instance will give it ID, instance ID 1, 2, 3, whatever. Okay? So construct and identify multiple graphs over the same physical topology. This provides a way to provide paths based on different optimization objects. So for example, you could build a graph only goes over encrypted links. Okay? You could build another graph that goes only non-encrypted links. Non-encrypted will be much more faster. Encrypted will be very secure. Right? You could build it in mixed. Right? So if that packet needs to be transmitted over encrypted, and the encrypted is instance ID 2, then you go to instance ID 2 graph. Right? So you could have multiple graphs over the physical network. Clear? So a node can only join a single graph within an instance ID, but can be associated with several instances. So it transmits in one instance, but it could join multiple. So it has to decide where to send, right? This is helpful to build multiple routing topologies on a physical mesh network. All right. For example, non-critical traffic should follow a path providing battery-powered nodes. It's not a critical transmission. Why I have to send it through battery-driven nodes? Let me make their life longer Let me only send important data through the battery driven. All right? Where more critical traffic should follow a path of minimum latency, for example. Minimum latency. So it depends, right? It's your design. You are the network engineer. It depends on the application what you will do. So multi-topology, what time class finish? 12:15, right? Okay, okay. So another class of traffic can use paths leading to data aggregator. So why the data? So for example, you could indicate some of the nodes which are a little bit heavier to aggregate data. What's aggregate? To collect data. And instead of going always to the root or, while other traffic should avoid nodes not supporting link encryption. So routing decisions are more complex using a variety of metrics and constraints. So you could design it, metric constraints. You could build multiple graphs, depends on the user could use it. Okay? Within one instance, the routing topology can be segregated among multiple graphs. Alright? Yeah, as the node moves to another graph, it has to abandon its current parent set, recompute the new rank based on its new position, and do a new parent selection. So what we learn from here? The routing, as we know, it's always dynamic process. It's not that we build the routes first time and that's it, Okay, and the nice thing in here, you can have multiple graphs. Graphs in here for us means what? Multiple graphs, according to what? Metrics and constraints. Alright, metric and constraints. For example, if you have the network built, we have like thousands of nodes built for certain application and to run over barriers. It's common that some of them will deplete before the rest. So your goal, okay, we call it network lifetime. What is your goal? To make the network survive as long as possible. So if you have the proper network technique, all right, you could make the network live as much as it can, and the whole nodes work together until the last moment. So by avoiding, so for example, you have a node that is like very low in energy. Keep it alive. Try not to go through it unless you have to, because every bit you send is power consumption. It will consume more power. Okay. The less data you send, the longer it will live. Plus, you have the sleep, wake, awake technique. The sleep, it wakes up when it needs to transmit. So there's a lot of things you could do. Right? All right. Supporting dynamic routing metrics and constraints. So metrics and constraints, routing for LLM require a sophisticated routing metrics strategy driven by type of the data traffic. So what kind of data? Is it like bits? Bytes? It's much more than that. Is it? Okay. A metric is a scalar quantity. Scalar is a quantity used as input for the best selection, and constraint, on the other hand, is used as an additional criteria that you need to use. So metric constraints can be node or link based. So you could have them for the node, or you could have them for the link. Node, link. So the node could have a constraint and could have a metric. Link could have constraint and a link. The example for node level metric are node state attribute, node energy, etc. So this is an example for node metric and constraint. For the link level, like latency, how much delay you have, reliability, link color, all of these things. So you have these descriptions for the link, and you have it for the node. All right. Now let's talk about sorting and non-sorting. Let's talk about sorting and non-sorting nodes. I already explained sorting, not sorting, right? Sorting, non-sorting, right? So sorting and non-sorting, storing and not storing nodes, right? Storing, that has a memory, can save the table. Not storing, it does not. So each node at the edge of the graph, sends a DAO message to allow routing state to be held. Routing state. That means what? Routing state. To be held for a traffic to flow in the dimension. This means that each node in the network would have to store the prefix of the network. Okay? And this has memory implication and routing table scalability. And each node, since each prefix entry translates to a routing entry in the routing table. Some nodes in the network may have significant constraints regarding memory. There's constraints regarding memory. And may be incapable of storing routing entries because we have low memory. Okay? These nodes are classified as non-storing. Non-storing nodes, which, okay, non-storing nodes. So, alright, so, anyways, so for non-storing nodes, okay, everything has to go to the root and goes down. You could have a mixed mode of operations. Okay, mixed mode of operations like storing, not allowed. Either you have storing or not storing for the all right? So for example,
Sorry,
if-
excuse me. The fact that it's not allowed doesn't mean that it's not possible.
not allowed means not possible. So either the node has to be storing or not storing.
So
It cannot work sometimes storing and sometimes not storing. Okay, it has to make up its mind, right? Storing or not storing. So for example, in here, in non-storing mode, when a node A sends a packet to node B, within the return domain, the packet first follows the graph up to the root, but not storing. Does not have graph, right? Goes up to the root, okay, to get the routing information and so on. All the edges, the root and all that, this is storing. Have to be stored. But the leaves could be not stored. Okay? Anyways. Okay, then the mechanism also for loop avoidance and loop detection. Sometimes you go through loops. And this is by all the networks you have to prevent. Whenever you have a trees, you could go through, end up with through a loop, right? A loop. I mean, anybody who uses a GPS sometimes will end up into a loop, you know. So what you have to do, you have to not to listen to it, right? So Ripple does not guarantee that absence of loops, but rather tries to avoid them and specifies mechanisms to detect the loops via data validation. Two rules for loop avoidance. Number one, as part of the max depth rule, a node is not allowed to select as a parent and neighboring node that is deeper. Cannot have deeper parent node. Has to be higher. That means the rank is this. Okay? i.e. whose rank is greater. Such that the node will end up advertising a value node rank plus the max depth, where max depth is the configuration value. Okay. So if you're looking for a parent, your level, your rank is 5, and you're looking for a parent. So you don't advertise for nodes 6 and 7 and 8. You advertise for nodes
4, 3, 2.
4, 3, and above, right? You cannot go down, you could go up. But rule number 2, a node is not allowed to be greedy, like us, okay, and attempt to move deeper in the graph to increase the number of parents. So some of the nodes try to go deeper, you know, okay, instead of rank 7, makes it 9. If it's 9, then you have much more parents, right? Much more parents, right? Okay.
Sorry, excuse me. How? I didn't really get that. How does the node get greedy?
So for example, here, so this is now, is what? 0, 1, 2. How about, instead of connecting like this, connect with that here, it presumes that it's deeper. Okay, so now it will be this in here, 0, 1, 2, 3, 4. So now instead of being 3, connected this becomes 4. Okay. So Ripple does not guarantee the absence of loops. We will cover it, right? Okay. Loops and LFNs are vital since there is a need for detecting these loops in addition to loop parts. So if you have a loop, you have to detect it, and then you have to fix it. One way to achieve this is by setting bits in the Ripple routing header and processing these bits as part of the data map. So header has a lot of information. Part of the header will have some information about the loops. When it's detected, then you try to fix it, right, in the header. So the idea is to set and process these bits as the packet moves up and down along the edges of the graph and check for anomalies in the various loops. For example, loops in the DAO path can be detected by using down bits in the Ripple routing header. So if down, it could be, you know, you flag one of the bits. If it's 1, it's down. If it's 0, it's up. You can detect it's a loop. All right. So if the packet, for example, how you know if the packet is up down, then after that it's up. Then when it goes to the next up, it's down. Then up, then down. What is this? It's a loop. Right? So if you are sending the packet up, so what is the route should be? Up, 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 up. Right? Or down, it has to be down, then down in the packet, down, down. Or if it's up, down, up, down, up, down, what will that mean? That's right. Or it's up, 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 down, 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 up, 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 down, down. What is this? Loop. Okay? So by setting certain information in the header that indicates the direction, for example. When a node sends a packet destined to one of its children in the down direction, it sets the down bit and forwards the packet to the next node. Upon receiving the packet with the down bit set, if the routing table looks up for the receiving node, indicates that the packet has to be forwarded up direction. This indicates it presses down, okay, we created a very clever, right? Very clever, okay? Alright. Alright, so the global and local repair. Repair is a key feature for any routing protocol and refers to the ability to repair the routing topology when failure occurs. Failure could happen, okay? How to, okay. Cellular Ripple supports a graph repair mechanism in the case of late and failures. Ripple specifies 2 techniques which are complementary in nature. Complementary, they assist each other. Okay? And actions. Local and global repair. Local and global repair. When a link or a neighbor node failure is detected to be unavailable and no other router in the up direction, local repair is free. What is local repair? Just connect to your neighbor and the parent of your neighbor becomes right? Local, right? Global repair is a repair mechanism that develops the graph from scratch. Cancel, delete all this, build it again. So of course, which one you have to try first? The local. And then after that, the global. If you cancel, we'll go to global. Okay, there is timer management. So, we have to, you have to control the energy. It is imperative to limit the control plane traffic, control plane packet. What's control plane packet? The data used just for controlling, not for data. So again, what we said that these nodes will communicate 2 kinds of information: real data and control information. If you will keep transmitting this control information, what will happen? We deplete, we deplete the energy for nothing. I mean, just for the controlling. Okay, exactly like when I need to come to give you a lecture for an hour, 15 minutes. Okay, so at the beginning, what I have to spend 5 minutes to sit on. That's for controlling the lecture, right? What if I spend like 45 minutes to sit on, and then I speak for half an hour? right? So most routing protocols use periodic keep alives, routing protocol keep alive protocols such as BDF to maintain routing adjacency and to keep routing table up to date. But this would be costly and elsewhere resources are there. You know, in OSPF in the regular, okay, the routing keeps always checking. Whenever there is an update, you know, frequently update the tables. I don't want to do that a lot in this kind of networks, right? Because the whole process consumes a lot. Just be cool, you know, be cool. As long as it's working in the data, you know, you don't have to optimize to the best, okay? The best optimization you need in such networks is what? Working. Keep the network working. And the message delivered, even a little bit late, okay, that's fine, right? So Ripple uses an adaptive timer mechanism called trickle time. This mechanism controls the sending rate of the DIO. So we have to control the sending rate of DIO to reduce the number of controlling messages, right? Controlling messages. You don't need the nodes to keep talking with the messages that's for controlling, you know, controlling, right? So the algorithm trees building of the graphs as a consistency problem and its use of trickle meters to decide when to multicast DIOs. So reduce it, keep it down. And this is this. Certain events are treated as inconsistencies in the inconsistencies in the network. So that's example of multi-topology routing using the Ripple routing. So here, for example, I'm seeing here physical topology. This is the edge router that's connected. So this is that instance one, this is that instance two. So you see, instance one is different than instance two. It's different maps. So this, for example, if you look at this, for example, okay, it's part of instance one and instance two. But you know, it only can operate in one of them at the same time. So this is poor equality. So you could build from a poor equality, fair equality, good equality, latency. You have the latency, some of them. Anyways, so that's what the. All right. So we spoke about a great protocol called Ripple. Okay, the Ripple is replacing the regular routing protocol that we have in the networks. All right, thank you.